Okay, welcome back. This is Mr. Hassan's Maths channel. I'm now answering question 4 part B from the specimen paper of the Pure Mathematics P3 International A-Level Cambridge exam, which is 9709. And this question here is about iteration, and in the first part here, numerical methods. So 4 part B and C will be answered on this video. The previous part of this question, 4 part A, is all about differentiation and the quotient rule and stuff, and that has already been answered, and you can watch that video as a separate video. I save them separately because I want to save the videos according to topics as well as the paper. So at the end of this video you'll see a link here for the specimen paper playlist. You can go to that and you can find 4 part A if you need to watch it. Now for 4 part B, it says verify by calculation that this equation, means the equation that we had to prove or show in part A, has a root between 1 and 2. So this is the equation that we had to show, and we have to show that this equation has a root between 1 and 2. So when you have a question like this, you have this equation. First of all, you rearrange the equation so it says equals 0. So you can do it in either way. I can write a minus a half times 3 minus ln a equals 0. If I want to make it simpler, I can multiply both sides by 2 even if I wanted to, and that's fine, but I can leave it like this. Now what I can say is, I can say therefore, let's call this a function f of x, or in fact in this case it will be f of a because the variable is a here, is equal to a minus a half times 3 minus the ln of a. Now I want to show that this equation has a root somewhere between 1 and 2. Okay, this is the same equation as this basically, as you can see. So I want to show that this is equal to 0 somewhere between a equals 1 and a equals 2. Now the way to do that is as follows. Okay, so we can choose the value of a as 1 and choose the value of a as 2. And what we do is we replace those values of a equals 1 and a equals 2 into this equation. And so we see, for example, what do we get when we put 1 into this equation? In that case, you're going to have 1 minus a half times 3 minus the ln of 1. Now that's going to give you 1 minus 3 over 2 minus 0. So it'll be 1 minus 3 over 2, which is 1 minus 1.5, which is minus a half. So we can see when x equals a or a equals 1, you're going to be somewhere down here. It's going to be a negative value. Okay. Now, if there's a root somewhere between 1 and 2, then the graph must pass through the x-axis between 1 and 2, which means when we put a equals 2 into this, it should give us the opposite sign. There should be a change of sign between these 2 points. If there is a change of sign between these two points and it is a continuous function like it is, that means that a root must exist somewhere between 1 and 2. Okay, somewhere between 1 and 2. So when I put if I put 2 inside this function, I'll have 2 minus a half times 3 minus ln of 2, which gives you 2 minus, and this is going to be 3 over 2, and now minus a half times minus ln 2 is plus a half ln 2, which gives you 2 minus 3 over 2, which is a half, plus a half ln 2. And we know that this is positive. If you want to confirm it, you can use your calculator and confirm it. You can say 0.5 plus 0.5 times ln 2, and it should give us a positive value, which you can see 0.8465, 0.847, 0.847 to 3SF. So we can see therefore this is positive. We can see this is negative. So what we should write is a little statement to just explain, say as, and what they're looking for is this little phrase: there is a change of sign between f1 and f2, therefore the root must be between a equals 1 and a equals 2, something like that. Okay, so the root must be between a equals 1 and a equals 2, or we can say between 1 and 2 if you want better. Okay, so the root exists somewhere between 1 and 2. Why? Because the graph passed through the x-axis between them. Must have passed it. If at 1 it was negative and at 2 it's positive, then somewhere between 1 and 2 it must have passed through the curve. Even if at 1 it was positive and 2 was negative, the same thing would have happened. We would have said between 1 and 2 this passes through the x-axis, therefore when it passes through the x-axis, what's called the root must exist there. So that's what we should do. Just rearrange this so it says equals 0, write it as a function with that variable, and then replace the a with the values that they're telling you to use, and you get your answer. Okay, so there's part B of 4, which is to do with numerical methods, and part C is to do with what's called iteration. So it says use the iterative formula an plus 1 equals a half times 3 minus ln an to calculate a corrected 2 decimal places, showing the result of each iteration to 4 decimal places. So the iterative formula basically helps us to home in on the root itself. Okay, so you always have to start with a point close to the root, and you normally use an iterative formula when it's difficult to actually find the root using algebraic methods. You use numerical methods. So what we do is, we know the root lies somewhere between a equals 1 and a equals 2. So a good place to start would be to use the first value of a as, for example, 1. I guess we could also use 2 as well. And then that will help us, as long as you're close to the root, using this, the first value which is close to the root, will help us basically focus in on what the root is. And this iterative formula will help us to do so. So if I know that a1 is 1, I can find a2 by replacing a1 inside this function as 1. So I can say a2 therefore is going to be a half times 3 minus ln of a1. Okay, so a2 is going to be here a half times 3 minus the ln of 1. Now we know that the ln of 1 is 1. We already worked out this is 3. This is going to be 3 over 2. Okay, so that's going to be 1.5. Okay, it says to 4 decimal places. Well, I'm not going to write this to 4 decimal places because it stops there. You don't need to. Okay, now for a3, you're going to have to replace a1 with what a1 is. So a3 will be a half times 3 minus the ln of a2, which is a half times 3 minus the ln of 1.5. And then we can find out what that is. Now, instead of having to do that again and again and again and again and again, okay, like write this out and do this calculation on your calculator, there's a nice little shortcut which you can use. So I'll show you how to do that. So what we can do here is we can write, I'll leave some space here. We can write here, what I'm going to do first, I'm going to use a equals 1 as my first value. So I'll press 1 and I'll press equals. That's now stored in my calculator as the answer. When I press equals, that's the answer in the calculator. So I can set this up using a half 1 over 2 times, then I'll have 3 minus the ln, and I'm going to put answer. Close the bracket and that bracket. So a half times 3 minus ln answer. Now because I press 1 and equals, the answer now stored in my calculator is a number 1. So if I press equals, it's going to give me a2, which should come out as 1.5. As you can see, it did. Now I want to now keep putting the new value of x in this place where it says a1, where it says an. I want to keep putting the new value of a into there every time. So if I press equals now because when I press equals, what came out was 3 over 2. That's now the last answer in my system, in the calculator. So if I press equals again, it's going to actually do this calculation for me, and as you can see, it comes out as 1.29726. Now we've got to write this to 4 decimal places, so that's 1.2973. 1.2973. Okay, so that's getting closer to the root now. It's going to help us get closer and closer to the root. So now I'm going to just write a4, and I'm going to write just equals. Now it's pretty obvious what I've done. You don't have to now write this whole thing out again. I'm just going to press equals. That gives us 1.3699. 1.3699. I have to keep going until it kind of settles down. So a5 is going to be, press equals again, 1.3426. 1.3426. So we want to go until we've got the answer corrected 2 decimal places. It looks like the first decimal place seems to be sorted out as 1.3 something, or maybe, let's see what it becomes. Press equals again to find a6. It's 1.3527. So A6 equals 1.3527. Okay, so it's settling down to 1.3 something maybe. Let's have a look. Equals again 1.3489. So again 1.3489, which is also to 2 decimal places 1.35. So it's seeming to settle down at 1.35. We can try it a few more times. 1.3503. It looks like it's going to be 1.35 to 2 decimal places. We can again just make sure. Let's do one more time. 1.3498. So again 1.35. 1.3498. Again 1.35. Let's just do one more time and see what we get. 1.3500. It looks like it's settled down. 1.3500. So we can say therefore A is equal to 1.35 to 2 decimal places. Okay, so there's the answer to part B, showing the result of each ratio to A to 2 decimal places. And if you wanted to just make sure, you can just keep pressing equals and you'll see it settles down eventually until it stops moving, and you can see to 2 decimal places it will end up as 1.35 when you round it. So we can, we can stop there and it'll be fine. So there's your answer to question 4 part C. Alright, so there's your answer. Now sometimes they might ask you to justify that this is the solution to 2 decimal places. Okay, that this is a solution to 2 decimal places. Now, if they ever ask you to do that, and they do in some of the Cambridge Edexcel questions, in Cambridge, I'm not too sure right now, but just supposing they do. If this is the root correct to 2 decimal places, okay, then we got to think about what this could have been before it was rounded to 2 decimal places. What could be the lowest that this could have been and the highest it could have been before it's rounded to 2 decimal places. It's going to be somewhere between these 2 values, okay, which would be the lower bound of this number, which is going to be 1.345. That's the lowest it can be, okay, before when you round it to just 2 decimal places, it's going to give you 1.35. And the highest it can be would be everything up to 1.355. If there's anything just below this, it's rounding to 1.35. So that doesn't include this number itself. It includes 1.34999, whatever that would be. That would round to 1.35 as well. So if the if we can show that there is a change of sign between these 2 values, then we know that the root must lie somewhere between them. Okay, we know the root must lie somewhere between those 2 values because the curve would have crossed somewhere between them, and that value when you round it becomes 1.35. If it landed over here, it would round to 1.34. If it landed over here, if it came over there, it would go to 1.36. Okay, but if it's anywhere between those 2 values here, it will round to 1.35. That's the lowest it could be, that's the high it can be. Okay, if between those values there's a change of sign, that means somewhere between them it's crossed the x-axis at that point and it will round to this value. So you can choose 1.345 and see what that gives us, and you can choose 1.355 in the original equation that we had here, this one here. Okay, so if we take this equation, the one that I wrote here, does this move? Okay, let me just do it like this, copy and paste down here. Okay, we take this equation. Okay, let me put it down here. Okay, and we put these values in. I'll just put them in. So we're going to put 1.345. So we have 1.345. Okay, minus 1/2 times 3 minus the ln of 1.345. Press equal, another bracket there, equals. That gives us a negative. So it's a negative 0.68 times 10 to the power of minus 3. Negative, just get my pen ready, negative 6.80 times 10 to the power of negative 3. So that's negative. Okay, and here we'll see what we get when we put 3.555, and on this side 355, and we see we get positive. You get positive 6.90. 6.90 times 10 to the power of negative 3 as well. Okay, so we can see there that again we can write, as there is a change in sign between these two values, then a root must exist somewhere between them. Okay, so that's not actually required in this question. Once we've got to this, we've finished. That's a bit extra that I've gone into in this question. It's possible that they might ask you that in other questions. Okay, but that's how we can deal with this question. All right, sorry about that, hold on. Okay, so that's how we deal with this question. So there we have it. That answers this question about iteration and numerical methods. Other questions from this paper can be found in the playlist that will be appearing over here at the end of this video. Other questions from this topic of iteration and numerical methods from my P3 Cambridge collection can be found over here. Other questions from numerical methods and iteration from my edXL, which has a lot more material in it, can be found in the playlist over here. You can subscribe to my channel by clicking on this link. Thank you for watching, and see you soon.